Okay, we want to do an example of a polar integral. Let's just take f of theta equals sine theta, theta from 0 to pi. Now this is easy to graph. Turns out it's a circle of radius 1, the low point at the origin here, center that what would in rectangular coordinates be 0, 1/2, or in polar coordinates it would be pi over 2, 1/2 pi over 2. Anyhow, coordinates of the points around here. To graph this, we think of taking a theta from 0 all the way around to pi. And we use some sample values of theta, pi over 6, pi over 3, pi over 2, 65 pi over 6, 2 pi over 3, 5 pi over 6, and then pi. So when theta is pi over 6, sine of theta is sine of pi over 6, which is 1/2. Sine of pi over 3 is approximately 0.87. It's exactly the square root of 3 over 2. Square root of 3 is 1.732. Nobody in my generation could ever forget that. And then sine of pi over 2 is 1, and so forth. So we have these points. 1/2 pi over 6, square root of 3 over 2, pi over 3, approximately value 1 pi over 2, and so forth. And we have a smooth curve. And of course, when theta equals 0, sine of theta is 0. So at this angle, or at this angle, theta is going to be 0. So we're going to have the origin. Okay. Well, there's our picture. Other polar graphs can be a little more complicated. This is one of the simpler ones. Still, whatever your function, you're going to do essentially the same thing. Okay, well, to understand what we're doing with the integral, we imagine breaking this up into a bunch of partitions, or partitioning theta. Okay, so in partition theta, we get a bunch of wedges, if you wish. And here's a typical one, not particularly well drawn. But now we bring this out here and we draw it down here. Okay, so there's our wedge. And this is actually the arc of the circle. But if we're thinking very small theta, the arc of the circle is not going to have much room to curve, much time to curve, much change in the parameter to curve. Okay, so here's the wedge, if you wish. Okay, so we have theta equals theta sub I minus 1 here, theta equals theta sub I here, where I is some index corresponding to our partition. And then we partition R. Okay, we partition R along these arcs of the circle, along the circular arcs, so that we have little segments like this. And here's a typical one. Now, our partitions from what? Our partitions from 0, because this thing tapers down to the origin. Then it will partition from 0 to what? Well, the maximum value of R is going to be determined by your theta sub I star. Whatever our function is, it'll go to f of theta sub I star. In this case, the function is the sine of theta. So we have the sine of theta sub I star. Typical element of the partition. Bring that out here. And sketch it. Exaggerating, maybe exaggerating the curvature. Exaggerating the fact that these lines get a little further apart. But as we've seen previously, you have a delta R sub ij here. And look back at what we did previously. I is the index for your theta. And then you have to have a J index for your R, and the J interval is going to have width delta R ij, which of course equals Ri J minus Ri J minus 1. Think about that. You want to understand that. You want to be able to construct this yourself. Okay. Now, what's the width of this thing? Of course, the width varies from here to here. But at the sample point, let's just say here's a sample point. Now, put a quarter to the sample point. I don't want to label it right now, but it's going to, the theta coordinate is going to be theta sub I star, and the R coordinate is going to be R sub I j star. Okay, and the R sub I j will be approximately, well, I don't have to worry about it right now. Okay, so anyhow, there's our sample point. I guess maybe I can label it up here. Won't be in the way. And at that sample point, how far is it across here? This arc distance it's okay, it's on the circle. So if we have our sample point here, this thing is on a circle of radius Rij star. The angular increment here is delta theta sub I. So by the definition of the radian, the arc distance here on this arc is Rij star delta theta sub I. By definition of a radian, just the arc of a circle cut by a given angle, corresponding to a given angle. If delta Rij is small, as it will be as we approach the limit, there's not much difference between this arc distance, and this arc distance. Also, the arc distance, the arc itself will be almost a straight line. Well, you put that together, and you see that the area of this thing is pretty much just the area of a rectangle. Now, why a rectangle? Well, it's because your radial lines from the center of a circle and the circular arcs make a right angle at any point. Any radial line makes a right angle with the arc of the circle. So that these are all right angles, so this is approximately a rectangle. So the area is Rij, which is this dimension, multiplied by this dimension. This is like the length and the width of a rectangle. And it's delta Rij, not just Rij. And of course, we can then write that as Rij star delta Rij delta theta sub I. Now, you don't have to do all this every time you do an interval, but you want to kind of think it through every time you do an interval. You want to remember what it is you're doing, because later on you're going to need to understand what it is you're doing so you can set up the intervals you need. Well, your typical region then, your theta is between 0 and pi. Instead of theta, now we're just going to say theta runs from 0 to pi. So theta runs from here to here, and R runs from 0 to sine theta along any value of theta. The area increment is established by this is R d theta. Okay, so now what do? Our integral is the integral, in this case from 0 to pi, because theta goes from 0 to pi, and for any given theta, r goes from 0 to sine theta. And then it's the area increment, the r delta theta, which of course in the limit we write as r d theta. We integrate it in this form. We integrate r dr from 0 to sine theta, which with the result of that integral depends on theta. And it's going to be sine squared theta over 2. And then we integrate that from 0 to pi. It's very straightforward to integrate r d theta. The antiderivative of r with respect to r is r squared over 2. And then that's evaluated between 0 and sine theta. And that gives us what I just said, sine squared theta over 2. d theta. Okay. And then you can do the integration, but any one of the number of techniques. Okay, so sine squared theta over 2 d theta integrated from 0 to pi. And it turns out that that's going to be pi over 4. Which is, of course, the area for this circle. Again, the procedure comes down to this stuff here. It really comes down to simply, if you have an f of theta, you've got to integrate r d theta, where r goes from 0 to whatever that f of theta is, in this case sine theta, and then theta is going to go from whatever lower limit to whatever upper limit you might put on it. So if you want the area of the circle between pi over 6 and pi over 3, you just go from pi over 6 to pi over 3. If you want the whole circle, of course, you do what we just did. If you want the half circle, of course, you're going to get half the area of the circle, which would be pi over 8. Okay, anyhow, do the integrals, understand how this extends, understand particularly why your area increment is r d theta. Okay, it's because the width of this some sort of rectangular increment within the no longer a strip, but it's a wedge corresponding to 2 values of theta. This arc distance is equal to the r times your delta theta. And this almost looks like it's all put together. So just put a little different boundary on it. Keep thinking about that as you do these problems.